If we're in a situation where we can't use F equals mg, it makes sense that we wouldn't be able to use potential energy as mgh. We'll have to find a new expression for potential energy, and we can use the work energy theorem for that. Also, a notational point, most books at this point stop using PE for potential energy, and they use either capital V or capital U. I don't really know why they do that at this point, but they do, and you should just consider all three of them to be equivalent. I might use any of them. So the work energy theorem says what we would have to do is integrate this force dotted into the displacement. This tells us that, again, only the distance radially matters, since that's really a dot product. And what we get is this expression for potential energy, negative G m1 m2 over r. One common mistake that students make is they will use this with r squared on the bottom when they want potential energy and vice versa, so you have to watch that. Since G and the mass and the distance are always positive, that tells us gravitational energy is always negative, or at best zero if we have two things infinitely far apart. This makes sense because if we have to separate two bodies that are pulling on each other, we're going to have to do some work. We're going to have to invest some energy to separate them by an infinite amount. This potential energy only makes sense between 2 points, just like MGH only made sense between 2 points. We used to use the lowest point an object could reach as our zero potential energy, but now what we use as our zero is infinity, and what that says is two things infinitely far apart shouldn't affect each other. So what's the gravitational potential energy of a 100 kilogram person on the surface of the Earth? We put in the numbers. Remember, we're not squaring this radius on the bottom. We get negative 6.25 times 10 to the 9th joules, and that means if we want to take that person and remove them infinitely far from the Earth, we have to put in 6.25 billion joules of energy. How fast would we have to throw the person if we imagine they're a projectile to do this? And this, of course, we're going to ignore air resistance again. We use conservation of energy. Initially, they're going to have this potential energy we just found, and whatever kinetic energy we give them, we'll call this velocity that we have to find, the escape velocity. When we get to infinity, if we play like that's a real place, the potential energy term will look like this, and the kinetic energy term will look like this, where we have 1/2 m v final squared. However, we don't have to have any particular velocity once we're infinitely far away from the Earth, so Vf can be set equal to 0. This will also equal 0 to the potential energy at infinity. So that means E at infinity is 0. Conservation of energy tells us E initial has to be the same as E at infinity, so we can set this up E initial equals 0. When we do this, we solve for the escape velocity, and we get square root of 2 gm E over RE, where those are the mass and radius of Earth. This is about 11 kilometers per second for the Earth. Also notice it's square root of 2 times the minimum circular orbital velocity, the speed we'd need to throw that baseball to get it around the Earth. What about the energy something has when it's in a circular orbit? It's going to have both kinetic and potential. We just found its velocity earlier. Back here, we found the velocity of an object in circular orbit, and we know the kinetic energy, or rather the potential energy. So we have V is square root of G m1 plus m2 over r for the velocity. If m1 is the Earth and m2 is the largest satellite ever orbited, m2 still might as well be 0. So V is square root of G me over r. Notice this is not going to give us 7,900 meters per second in general, because this is r, orbital radius of the satellite, not necessarily the Earth's radius. Then we put in kinetic energy, 1/2 mv squared. Potential is G mm over r, again, not necessarily r Earth. We plug in our expression for V into this, and we get this. We do a little math, and we see that we can actually get a common denominator. And when we combine these things, we get negative G mass the Earth, mass the satellite over 2r. So anything in circular orbit is still going to have negative total energy, and that's what's called a bound orbit. It can't just leave. You have to invest energy. What we can use for this, what if we have a 1,000 kilogram satellite in a warehouse on Earth's surface, and we want to move it to a height of 35,800 kilometers above the surface? That's an interesting height that we'll see later. The way we would do this is to use conservation of energy. So if we use conservation of energy, the energy of the probe on the surface of the Earth, when it's in the warehouse, it has no kinetic energy, it has only gravitational potential energy. Notice we don't have a 2 here because we're not talking about something in orbit already. The R value is radius of the Earth. We calculate the total energy and we get negative 6.25 times 10 to the 10th joules. Once it's in orbit, we'll have both potential and kinetic energies, but we don't have to find them separately since we already have a formula for the total energy of something in a circular orbit. And here, notice we have a 2 on the bottom from that formula, and R is the radius of the object's orbit. So in this case, it's altitude, 35,800 kilometers, which is several Earth radii, plus the Earth's radius. Total energy in this orbit is negative 4.73 times 10 to the 9th joules. We can tell this is significantly smaller than what we had before in absolute size, so we've done most of the work to move this satellite off of Earth forever. The difference in energy is 5.78 times 10 to the 10th joules. And of course, in reality, it's going to take much more energy than that. We've ignored air resistance, which we can do after a certain altitude, but we certainly can't do it during the launch phase. Although there's been talk of people firing satellites out of cannons like projectiles, they're not doing that yet. They travel on rockets. The rocket has a large mass, and so does its fuel, and all these things have to get off the Earth's surface to varying heights. This also shows you the reason why we launch rockets from Florida and not the North Pole. The Earth has a circumference of 40,000 kilometers. The original definition of the meter is actually 1/10 millionth of the distance from the North Pole to the equator, and it rotates once in a little less than 24 hours. So a point on its equator moves at 464 meters per second, which is faster than the speed of sound. As we move towards the North or South Pole, the surface speed drops by a factor of cosine of the latitude, so if we're up at the Arctic Circle, the ground speed is only 185 meters per second. If we launch a rocket to the east, we get to use this free kinetic energy, and it'll take a little bit less fuel. We would put that here in the total energy on the surface. So we would make this a little bit less negative.